Welcome to our presentation. I'm Mike Brownson, Director of Business Development for In-Building Wireless and our Public Safety Product Line Manager at Westel. This presentation is an introduction to public safety emergency responder radio communication systems. The video is intended for folks interested in learning more about the installation requirements of public safety in-building enhancement solutions, or perhaps for a building owner that's been told they need to have a system installed. In this webinar, you'll learn the basics of what is an emergency responder radio enhancement system, why they are being required in new construction, existing construction, and remodels, where to find the code sections that define these requirements, plus an overview of those requirements, the typical process of the design and installation from start to finish, the common components used, and the skill sets needed to design and install these systems. So with that, let's get started. So let's start with what is public safety DAS? It goes by many different names. It goes by Emergency Responder Radio Communication Systems, or ERRCS, Emergency Radio Communications Enhancement Systems, or ERCES. You may even hear folks call them ERCs for short. They are also known as BDA systems, Public Safety DAS, DAS, which stands for Distributed Antenna System, or Signal Booster Systems. But regardless of the name, these systems are essentially a network of antennas distributed throughout a building, connected to an amplifier that is bringing in and amplifying the radio signals from the public safety tower site. Special attention is paid to certain areas of the building where a higher degree of reliability is needed, such as stairwells, exit pathways, areas of collection and emergency, standpipe locations, fire pump locations, and fire control room if one exists. Most cities across the country are now requiring that first responder radio communications networks be tested in new construction or major remodel. If the coverage is found to be lacking, then the fire inspector has the right to require a solution be installed to remedy the issue. To many building owners, this comes as a surprise because in many cities, this level of enforcement is new due to recent enhancement or adoption of the newer fire code. Public safety DAS requirements first showed up in the 2009 version of IFC, the International Fire Code, and then the 2010 versions of NFPA. Though certain cities around the country have been requiring these systems for almost 20 years. For example, some Southern California cities, along with Denver, Colorado, adopted radio enhancement solutions as part of their building code over 20 years ago. Like other systems in a building, it's ultimately the building owner that is responsible. In new construction, it's part of a life safety system, just like fire alarm and the sprinkler systems. Though fortunately, the ERC systems are typically much less expensive than those other systems. We find that often in new construction, the actual work is subcontracted out by the electrical contractor or the fire alarm contractor to a specialty contractor with radio frequency knowledge. So here's a list of acronyms and that we'll run into in this industry. As I mentioned, there's ERCs. NFPA stands for the National Fire Protection Association. They're an organization that writes model code. You also have the International Fire Code, which is a subset of the International Building Code, the FCC being the Federal Communications Commission. You'll hear me mention AHJ a lot. That stands for the authority having jurisdiction. Typically in this realm, it's going to be the fire marshal or the fire inspector. And I also mentioned that there's DAS, Distributed Antenna Systems, BDA. LTE is what's being used by FirstNet, stands for Long-Term Evolution. It's a high-speed data network. NRDL is a nationally recognized testing lab. TXRX, ULDL stands for uplink downlink. DAQ for delivered audio quality. Another question we often hear is, so how much do these systems cost? My favorite answer, well, it depends. Unlike other life safety systems, there are many variables that can impact the cost greatly. So aside from the size of a building, the other big impact is actually the frequency band that the fire and police use. Most large cities have migrated to the 700 or 800 megahertz band. The enhancement equipment for these bands is generally less expensive than for the lower frequencies in the VHF, UHF bands, where the cost of a 700, 800 signal booster may start at about $6,000 and upwards of maybe $12,000, $15,000. The cost of a VHF BDA I've seen range from $14,000 to well over $50,000, depending on how complex the frequencies are to accommodate. So you can imagine how a $50,000 BDA in a 50,000 square foot building would upset the cost per square foot formula. So there's really no clear way to say, this is how much it's going to cost. And then there's the rest of the components that go along with that, plus the physical installation. The other impacts of the cost are whether the city requires the cable to be installed in conduit, or is union labor required, or is it an existing building? Then the overall size and shape of the building will impact costs. For example, a high-rise is typically less labor than a courtyard-style apartment or a hospital. So cost per square foot can range from as low as 10 cents a foot to well over $1. But a reasonable rule of thumb is probably in the range of 25 cents a foot, unless one of the cost multipliers is involved, such as conduit, 2-hour fire-rated cables, or use in the lower frequency band. So here's a typical passive DAS system. Buildings of about 500,000 square feet or less can typically be covered by a single BDA feeding a network of coax cables, splitters, and antennas. Though for buildings that have a lot of interior walls or heavy wall materials, the maximum size could be much less. On the roof of the building is typically a donor antenna. The donor antenna picks up the radio signals from the tower site, feeds that signal into the BDA or bidirectional amplifier, also known as signal booster. The BDAs will amplify the incoming signal many millions of times higher and then sends that signal out another coax cable network to a network of splitters and indoor antennas. This assures that there's an antenna not far from the first responder and is radio providing clear communications to the dispatcher fire command center. EMS may also be used, these systems, to assure life-saving instructions are efficiently passed onto EMS personnel inside the building. Police radio traffic may also ride on these systems so they have reliable communications when responding to events indoors, such as domestic disputes. So you can see how important these systems are, not only for the emergency responders, but also for the civilians inside the building. So here's some typical venues for passive DAS. Big box stores, smaller hospitals, medium-sized office buildings, apartment complexes, self-storage units and such can be covered by just BDA, coax, and antennas. The other configuration that's common is an active DAS. An active DAS, where you still have the rooftop donor antenna going to the signal booster, but at the signal booster, the signal is then converted to optical fiber and sent to remote amplifiers distributed throughout the building. Then those remote amplifiers will feed coax cable antennas in that section of the building. So this allows a public safety DAS to cover many millions of square feet of floor space, or even multiple buildings in a campus or residential complex. And for the typical buildings that they'll cover, obviously large office buildings, malls, large hospitals, college campuses, stadiums, casinos. Again, typically 500,000 square foot and up. Again, if there's higher density walls or there's a lot of clutter inside, it could be a lot smaller, may require an active DAS. So let's take a moment and let's talk about the code base. So it's often said that the Twin Tower tragedy in 2001 started the whole public safety DAS mandate. And perhaps it did spur some things along. But as I mentioned earlier, the movement was already underway. But in 2009, the International Fire Code included emergency responder radio enhancement requirements in Section 510 of the Fire Code. The next year, NFPA added a section to NFPA 72 with some similar language. So as cities adopted these newer codes, the requirements to test radio coverage shows up. And then over the next few years and over the next few revisions, the language has been expanded upon and further clarified. NFPA has since moved this requirement to their NFPA 1221, and in the 2022 version is being moved again to NFPA 1225. So regardless of where the code is, it's pretty much stayed the same, with minor revisions along the way. So earlier versions of the code called for a minimum radio signal level. Typically is neg 95 dBm. That establishes an RF level. This number represents a radio signal strength suitable for reliable radio communications in almost all instances. However, as time goes on, it was decided that voice intelligibility was actually much more important than just signal level. After all, what really matters is whether first responders can reliably communicate. So DAQ, or delivered audio quality, was established as the preferred measurement. The measurement is now that clear radio communications must occur with a minimum need to repeat, defined as a DAQ of 3 to 3.4, depending on the code version. But ultimately, this is a somewhat subjective test. So it does depend on the fire inspector at the time of inspection. The next requirement is that a high majority of the floor space must meet this minimum coverage level. So IFC calls for 95%, while NFPA calls for 90%. However, the inspector will likely demand a much higher degree of reliability in critical areas. Other typical requirements spelled out in the code is that the signal booster must have FCC certification, which they pretty much all do. They must be connected to the fire alarm panel, so if there is a failure, it'll send a supervisory signal to the fire alarm monitoring company so that a repair can be initiated. Also, BDAs must have a battery backup system in case power is cut to the building. There's also a lot of language in the code surrounding cable pathway survivability. Because if a coax cable is interrupted by either physical damage or fire, then the whole system becomes useless. So protection of those major pathways is prescribed by the code. There's a lot more to it, and the actual requirements can vary a bit depending on the jurisdiction. It's one of the challenges to an IRCS install is that the changing aspect of installing the public safety BDAs due to the differences in what the inspectors are looking for. So having an installer that's familiar with the local code requirement can save a lot of time and hassle. So let's talk a little bit about UL, the Underwriters Lab, Standard 2524. So it's the new UL standard for safety that specifically covers signal booster systems for first responders. Though let's know that it only covers the active powered components. Doesn't cover the cables, doesn't cover the antennas, doesn't cover the design or the installation. So UL 2524 doesn't really say that a listed system is going to work better than an unlisted system. But it does mean that it went through a series of tests by an independent certified lab to verify that it meets safety standards. Westel started shipping our first 2524 listed product in June of 2020. This will become more and more important as more inspectors require UL listed equipment. The next versions of both the IFC and the NFPA code will actually be requiring this UL listing in the future. I earlier mentioned the difference in cost of BDAs depending on the frequency band. So let's spend a little bit of time talking about frequency bands. So here's a description of the bands used. Okay, the VHF band, sometimes used by public safety networks, is between the 150 and 174 megahertz RF spectrum. So this band is actually a little bit above the FM radio band that you have in your car to listen to news, sports, and music. The signal will travel long distances, but the amount of spectrum is limited, and there's a lot of users of all sorts, not just first responders. Due to congestion in this band, many cities have moved their radio systems to higher frequency bands. The UHF band covers from 450 megahertz to 512. However, channels above 450 are only available in a few cities around the country. Now, the most commonly used frequency band for first responder radio networks is the 700 and 800 megahertz spectrum. Systems in this band are typically using the latest technology with more efficient spectrum use. The spectrum is actually very similar to that used by cellular networks. Now let's talk a little bit about FirstNet. You may have heard about that. It's a nationwide LTE network operated by AT&T. It provides high-speed data, providing priority and preemption to emergency responder organizations. But when it's not being used by emergency responders, it's actually available for you and I to use on our cell phones. Now that you have a foundation of what a DAS is and the code base that mandates it, so let's talk about the process of installing a system. Okay? The process shown here is typical for new construction where competitive bidding is done. Oftentimes at the start, there's not even a building to measure, we just have a set of plans. Regardless of the situation, the most important aspect to know is what the HJ wants. This includes what frequency bands they're on, what code base they use, and any special requirements that they may have. Now, many cities will even publish a guideline document, especially for radio enhancement systems. So it's important to reach out to your local HJ and verify their requirement before getting started. So we'll walk through a few of these steps in more detail in the following slides. They cover testing and design and installation process. But at a high level, you need to collect some basic requirements, plus take some signal level readings at the site in order to get a design done. The designer will also need a complete set of floor plans, and depending on the situation, may actually have to revisit that design a few times. First, as a very preliminary design to bid the project, then if awarded the project, there may be a more complete design done to review with the building owner and or architect. They may ask for changes such as moving the BDA to elsewhere or using a different cable path. The project manager may also find issues with a preliminary design that would impact cable routing or antenna placement, which then may require another design. So be prepared to revisit this step, possibly a couple of times. So take a moment to read through this list. Like I said, first and foremost, contact the HJ and the radio authority. Make sure you know what the requirements are. If there's a building in place, good time to take a site survey, take some baseline testing measurements. Then a preliminary design is done. If you're bidding a project, There's some basic information that's needed for the designer to create a budgetary design that you can bid. Once awarded the project, there's the contract work, which involves a statement of work so that everything is clearly defined. There'll be a more in-depth RF survey that typically has to wait until the structure is completely closed in. This survey is to determine what areas may already have good signal and you don't need to add an enhancement system. That may initiate another design update. Right, then we'll do a walkthrough with the building owner or the general contractor. Make sure everything is in the right place, which again may initiate another design review. Then you can finally order the equipment, install the gear, commission it. Be sure to get a retransmit agreement from the radio authority or the license holder. And then lastly, do the inspection with the HJ and sign off. So let's talk a bit about these site surveys I mentioned. There's two aspects to a site survey. There's the physical side, such as where does the BDA go? How do I get from one floor to the next? Do we have stacked riser closets with sleeves? It's also important that we take RF signal measurements. A rooftop measurement is needed so we know how much signal is coming into the BDA. It's also helpful to know what areas of the building already have adequate radio signal. If police and fire can reliably use the radios in the upper floors, there's no need to install antennas on those floors. I've seen very large buildings that only needed coverage in the basement, perhaps even 25,000 square feet or less. So this can greatly reduce the overall cost of a system. It's one reason that a price per square foot is so difficult to rely on. Anyone doing site surveys must have the right equipment. It's impossible for us to see radio waves, so we need specialized equipment to help us with that. So typical equipment may be a spectrum analyzer. It's used to measure RF signal strength across a spectrum of frequencies. There are also some portable two-way radios that can be programmed on the radio system and will provide an RSSI, or Received Signal Strength Indicator meter. There's also specialized scanning equipment that allows the surveyor to simply just walk through the building while it automatically collects RF measurements. So having the right tools and knowing how to use them is critical. So here's a couple examples of a pre-install survey, noting signal levels in various locations. On the left, the system integrator used a spectrum analyzer and just hand wrote notes on the floor. It's rough, but it's effective. On the right is a survey done with the PCTEL scanner that automatically tracks RF levels and creates a pass-fail grid. The green blocks are ones with a passing signal level, and the red blocks are failed signal levels that did not meet the required threshold. Designing distributed antenna systems is a specialized task generally reserved for those with an understanding of RF behavior and link budgets. However, with time, training, and experience, anyone can really learn to do well at designing systems. The industry has adopted certain design tools that really help with this process. Now, they won't design a system all by themselves, just like a CAD program doesn't design a building, but they do allow a designer to create a design, and then the software handles all the calculations and the documentation to make it easier. IBwave is the most common RF design software platform. RandPlan is another, and is a new entrant. If you're interested in purchasing one of these design software platforms, expect to spend at least $7,000 for a light version and upwards of $25,000 for design software with heat mapping. If you don't wish to take the plunge with the expensive software and the skills needed, Westel does provide preliminary design services, though depending on the HJ's requirement, you may still need to hire a professional if a PE stamp drawings are required or heat maps are required or CAD files are needed for permit submittal. So here's an example of a layout plan using IBWave. It shows the component locations and the identifications for the installer to follow. So the blue lines here are the cable routes. It shows the splitters and the antennas. So all of the components are laid out here with labels for the installer to follow. Also available is a riser diagram from these design software. The riser diagram will, again, different view of how everything goes together. It'll identify the component part numbers and IDs. It'll also show the signal levels. For a close-up view, you can see here the BDA and a few of the tappers nearby connected to antennas and the signal levels for each antenna. The software design program will also create a complete equipment list. So this will help in bidding and, of course, in ordering all the right gear. When undertaking the installation of a DAS system, there are several important considerations. Of course, a general mechanical ability is important, solid project management skills, but the installer really also needs to know how to correctly attach connectors to the coaxial cable. Improper connector installation can cause poor or intermittent operation, failure at inspection, or worse yet, failure during an actual emergency. Sometimes the issue may not show up for some time. So reliable install requires quality workmanship. The project manager must also be familiar with the IFC or NFPA code requirement that's in place for the local HJ to assure a hassle-free inspection process at the end. One of the most critical aspects of the installation is the final commissioning of the single booster. We'll cover that later, but it's especially important because an improperly commissioned BDA can cause serious interference to the tower site. Also be sure to understand the HJ's unique requirements. For example, if you find out only after the install that the cable was supposed to be running conduit, well, that's a big problem. It's also important that the installers follow the design as closely as possible. Changes to coax routing can impact the final performance, and the RF splitters must be shown or must be installed exactly as shown on the plans. So let's talk about the cables used. Typically, we use 1/2-inch plenum rated hardline for these installations. For those familiar with electrical cabling, it may look like BX type cable to you, with its corrugated armor covering, but it's actually quite different. It's much easier to damage, so care must be taken during the install. Any crushed, crimped, or twisted sections of the cable will act as an RF block and no signal will pass through. The cable also requires specialized connector prep tools. These tools are not too expensive and the cost is more than saved through the reduction in labor. You also need some flexible jumpers for connecting the cable to the tappers and such in tight spaces. And it's highly recommended that the coax cable be swept after installation. Sweeping a cable tests it for presence of faults. It's useful to assure that a cable was installed correctly and the system will work once complete. New to the industry are coaxial cables that come with a 2-hour burn rating, like RFS Dragon Skin or American Firewire. So if the HJ has a 2-hour survival requirement, these cables can save a lot of time and money. Other important components are the passive devices like the splitters, tappers, couplers shown here. These devices allow the radio signal to be split to multiple antennas evenly. Radio signal strength will actually decrease by half for about every 140 feet of cable. So to account for these losses, And to distribute the signal evenly to all the antennas, splitters, tappers, and directional couplers are used by the designer. The splitters are available in 2, 3, and 4-way varieties. They're used to evenly split RF between the output ports. Tappers and directional couplers are basically just unequal splitters. They come in a variety of values from about 1/3 the power out the tap port to 1/1000th of the power out the tap port. So it's vital that the installer use the correct value as shown in the design. An improperly installed tapper or coupler can result in a failed inspection. There's also filters that are available to filter out unwanted interference, and crossband couplers to break out various or combine various frequency bands. One of the most important stages of a DAS install is the commissioning of the BDA. Now, it's vital that the person adjusting the BDA understand how to do it properly, and they must have the proper equipment. At a minimum, they must have a signal generator and a spectrum analyzer to commission a BDA system, and of course, know how to use them. As mentioned earlier, improper installation can at worst cause severe interference, at best provide inadequate coverage, resulting in a failed inspection and delaying your certificate of occupancy. So if you're looking to get into the BDA install business, please take time to learn about RF and how to use the equipment, or hire someone who already has that RF knowledge. So here's an example of a post-install grid test. So the installation is finally done. You think you're ready for the inspection. So it's time to do a grid test as defined by the code or your local HJ. Typically, a building is broken out into 40 equal size grids per floor. An RF measurement is taken within each grid. This assures that the radio signal is being distributed throughout the building and to the levels as expected by the design. Once you're sure it'll pass and the installation has been cleaned up, the cable's tied down, everything's labeled, you're ready to call in the inspector. Good luck. And oh, by the way, don't leave the BDA powered up and operating. It's illegal to be passing a radio network's RF signals without getting permission first. And you want to be sure you're not going to cause interference. So let's talk about that a bit first. Okay. So before BDA can be turned on, you must get permission from the radio authority or the license holder. It's often not the actual fire department, but the local radio authorities that manages the radio network. The fire inspector can help direct you to the proper contact. Also written into the IFC code base is a requirement that the installer possess a general radio operator license, also known as a GROL, or GROL. It's a test given by the FCC that covers radio theory and radio law. So it's common for the HJ to require the installers have a GROL. Finally, if the BDA is a Class B type or a broadband amplifier, it must be registered in the FCC database. This is a very simple 5-minute task, but it allows the FCC to determine the point of contact if the BDA is found to be causing interference. And most importantly, so they know who to call to shut the BDA down so that it's no longer causing issues. Well, that covers everything at a high level. I hope you found this virtual tutorial useful in understanding more about public safety BDA systems. This has been presented by Westel, a manufacturer of public safety BDA systems for over 20 years. Westel offers one of the most complete product lines that includes nearly everything needed for a DAS installation except for the coax and connectors. We are truly the one-stop shop for everything ERCS related. We also offer distributed antenna systems for cellular coverage as well. So I'd like to thank you for taking the time to learn more about public safety DAS systems. If you have any questions, feel free to reach out to us. Or if you'd like further education, or you have a specific project you'd like to discuss. So thanks for your time, and feel free to contact us if you have any questions.